This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2017 AP Calculus exam, free response question AB4 BC4, namely separable equations. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the definition of a separable equation, and then I'll discuss the general solution technique for this type of differential equation. And I'll present several examples, typical AP Calculus type problems that involve separable equations. And finally, I want to make sure I discuss the absolute value notation when there is an antiderivative that involves a natural logarithm. This topic is related to the interval of definition, or sometimes called the maximum interval of convergence. First, a little bit of background. In AP Calculus, we study first-order differential equations from three perspectives: a geometrical approach, which involves slope fields; a numerical approach, which involves Euler's method; and now we consider a symbolic approach, in which we try to find an explicit formula for the solution to a differential equation. When we consider a differential equation, I think it's important to remember that we cannot always find an explicit solution. For example, a solution y in terms of x. However, in some situations, we may indeed be able to solve explicitly for the dependent variable. Here's a definition to begin our discussion. A separable equation is a first-order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. So this means that we can write the differential equation in the form dy dx equals g of x times f of y. So the equation is separable. The expression on the right side can be separated into a function of x and a function of y. Now, if f of y is not equal to 0, then we can write the differential equation in this form, where h of y is 1 divided by f of y. To solve this differential equation, we begin by rewriting it in differential form. H of y dy is equal to g of x dx. So now all of the y's are on one side and all of the x's are on the other side. Then we integrate both sides of the equation. Now this equation defines y implicitly as a function of x, but in some cases we can actually solve explicitly for y in terms of x. And without going into detail, it is the chain rule that's used to justify this procedure. That is, that we can integrate both sides of the equation and maintain equality. Let's consider a basic example in a non-contextual setting. First, let's solve this differential equation, and then let's find the particular solution of this equation that satisfies the initial condition y of 0 equals 2. First, rewrite the differential equation using differential notation. Then separate the variables and simplify on the right side. Next, integrate both sides of this equation. Integrate on the left side with respect to y and on the right side with respect to x, as indicated by the differentials. And here I used basic anti-differentiation rules. Note that I could have used a constant c1 on the left and another constant c2 on the right, but then we could combine them by simply writing c is equal to c2 minus c1. And finally, solve this expression explicitly for y. To find the particular solution, we let x equals 0 in the general solution, and we solve this equation for c. And here's the solution to this initial value problem. Note that it's often easier to determine the constant of integration immediately after integrating, and then we can solve explicitly for the particular solution. Here are some graphs of several members of the family of solutions of this differential equation. The blue curve is a graph of the particular solution. Here's a technology solution to this example. I used the TI-Nspire to find the particular solution to this differential equation. The calculator function is DE_solve. And on the right side, I constructed a slope field and added several graphs of the family of solutions. Again, the blue curve is a graph of the particular solution. I think this is a very nice visualization of this example. The geometry here confirms the symbolic solution. Let's consider another differential equation. And let's find the particular solution that satisfies each initial condition. So use differential notation and separate the variables. And then integrate both sides. Use basic anti-differentiation formulas and note that the left side here must have the natural log of the absolute value of y. In this example, I'll use the initial condition before explicitly solving for y. So use y of 0 equals 2e and solve for c. Now I can resolve this absolute value symbol. Since y of 0 is equal to 2e, the value of y is greater than 0, and the absolute value of y is therefore just y. Therefore, in this case, I can just drop the absolute value symbol. This particular solution is a branch in which y is greater than 0. We're actually finding the interval of definition, or the branch of the solution that contains this initial value. And then we solve explicitly for y. In part B, I used the initial value to find c. However, this time y is less than 0, and therefore the absolute value of y is negative y. And then I solved explicitly for y. Here's a technology solution to this example. I used the TI-Nspire again to find each particular solution to the differential equation. And on the right, I constructed a slope field and added graphs of the two particular solutions. I think this nicely illustrates the concept of the interval of definition and why we need that absolute value symbol. The sign of the argument of the natural logarithm, which is y here, really determines the branch of the solution. And here's an interesting open question. Can you describe the behavior of the graph of each particular solution as x increases or decreases without bound? Here are some other issues for consideration. What if the solution to the differential equation involved a natural log of a function of x? What do you think the branches of the particular solutions would look like? And remember that after separating the variables, one or both sides may not have a closed form antiderivative. Or we may have to use a technique of integration, for example, integration by parts. Separable equations can be applied to particle motion problems. We can write acceleration or velocity as a differential equation. And then we could separate the variables and integrate both sides. And there are lots of applied contextual questions involving separable equations on the AP Calculus exam. This example involves silver queen corn, one of my favorite varieties. Let's suppose that at time t equals 0, a seedling is planted with height 0.5 feet. If h of t is the height of the stalk at time t days after it's planted, then the rate of growth is given by this differential equation, where h is less than 8. Here are several questions in context. To determine if the stalk is growing faster when it is 2 feet or 4 feet, we need to evaluate the differential equation at both values and compare. Note that here I have the value of the dependent variable h, not t. And fortunately, the differential equation is given in terms of only h. So evaluate dH/dt at h equal 2 and at h equal 4. And since the value at 2 is greater than the value at 4, the cornstalk is growing faster when it's 2 feet tall. To find the second derivative of h with respect to t, we differentiate the given differential equation with respect to t. And don't forget the chain rule here. H is a function of t. Since 0.5 is less than or equal to h, which is less than 8, the second derivative here is less than 0. And therefore the graph of the solution curve is concave down for t greater than 0. To find an equation of the tangent line, we need a point and a slope. We have a point, h of 0 equals 1/2. This is the initial condition. And we can find the slope by using the expression for dH/dt at h equal 1/2. So here's an equation for the tangent line to the graph of h at t equals 0. An estimate for the height of the stalk at time t equal 10 days is 3.5 feet. And since the graph is concave down, the tangent line is above the graph of h, and therefore this is an overestimate. Let's find the particular solution to this differential equation. First, separate the variables. Note that there is no function of t here, the independent variable. And I'll keep the constant 1 divided by 25 on the right side. I just think this makes the integration easier. Integrate both sides, resolve the absolute value, use the initial condition, and solve explicitly for h. Let's suppose that the corn will be harvested when the stalk is 7.7 feet high. Find the value of t for which h of t equals 7.7. Now, I used a fraction equivalence here in order to find an exact symbolic answer. So bring the constants to the left side, take the natural log of both sides, and the value of t is approximately 80 days. Here are some technology solutions to this example. Here's the symbolic solution to the initial value problem. And here's a graph of the solution curve and the tangent line to the graph of h at t equals 0. One can visualize the concavity and that the tangent line approximation is an overestimate. And here's a solution to the equation h of t equals 7.7. I also constructed the slope field and a graph of h. I think this is a nice geometric confirmation of the analytical solution. I hope this video provides insight into separable equations, a few AP Calculus type problems, and the use of technology to solve these types of problems, especially those that are presented in context. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.